All right. Have any of you been listening for the weather, particularly? Is most of the danger of severe weather over, isn't it? At least up here. I think down south it may still have some. What's that?
They're talking about it later.
Okay. So I don't think we need to go over what to do in case the alarm goes off, because I believe most of the worst of it is past us. Okay. You do know what next Tuesday is, right? How soon you forget.
Election day.
Election day, absolutely. And if you, any way you can manage it, work it out so you can get by to vote, because I know y'all are going to be here until 7:45 in the evening, right? So see if you can register on your way in the morning. Vote on your way in, or register sometime during the day. But make a plan, see if you can do it. Now, if you can't, you might still be able to get an absentee ballot and get that done if you can't do it otherwise. So please try to always figure out a way to vote. Okay, anything else? Today I had hoped to make really good progress. I made some progress on getting spring schedule done, but because of several people coming by my office, telephone calls and other things, I didn't get nearly done what I wanted to. Michael is here. So I'll still be working on that tomorrow, but I hope to finish up the spring schedule tomorrow, and then maybe get some of this grading caught up, because my goodness, I can't stand having this many papers ungraded. Okay, good deal. Thank you. All right, so let's move on from there. How are we going to manage today? Well, it's a little after 3:15 now. I don't know what time it is actually. But we're going to go about 2 hours in class and then have 2 hours of lab. Your lab will not take you, unless you really dawdle, 2 hours to do the lab. But you'll have up to 2 hours to finish the lab, and then the last 30 minutes we'll have the test on Chapter 2. Now, if you haven't done your formula and equation sheet, that might be something you want to be putting together between now and 5:15 or whatever time, 7:15 or whatever time that would be that we have our test. So any questions on how we're going to do today, or proceed from now? All right, so let's get started in energy. If we don't get far enough in the chapter, we may not have the lab today, because this is the first lab in Chapter 3, and if we don't get far enough to have the lab, then we'll have to stop. Energy, what does that mean to you? Anything? Say again?
Power.
Okay. I was going to get to that. We're going to talk about power, and people use energy, power, sometimes force, sometimes work. We use them all as if they're the same thing. Actually, energy and work are close to being the same thing. Power is different. Force is different, okay? So you have to really pay attention to the use of words. In everyday English, yeah, we use the same sort of interchangeably, but not in physics, okay? In physics, they are very specific in their meaning. So the core concept here, and you'll find this on page 62, energy is transformed through working, there again, energy and work are related, or heating, energy and heat are related. And the total amount, I would say, but the total amount remains constant. Now, y'all got a good idea what this is? That's a dam, and it's, did you say Hoover Dam? Someone? It may be, I don't know. I don't think it's big enough to be Hoover Dam, but I don't have a great perspective of it. I think it is on the Colorado River, but I'm not certain of that either. What you got here is the water on the other side of the dam is probably up to about that level, and here it's down to this level, okay? What you're doing with the dam is backing up the water, giving it one type of energy, and that is gravitational potential energy. We'll get to that a little bit later. That gravitational potential energy, when it's released, falls, the water falls and moves quite rapidly, and that gives it kinetic energy. That's the energy of motion. That kinetic energy is used to turn hydroelectric turbines at the base of the dam, and that produces electricity, electrical energy. That electrical energy is then sent through the various towers here to various parts of the U.S. Okay? So you see right there at least 3 different energy forms, possibly even more than that. Gravitational potential energy of the water, kinetic energy of the water, and electrical energy being produced from that. Energy is transformed, but the total amount remains the same. You never gain or lose, create or destroy energy. It's always constant. It changes form at the flick of your wrist, but it still is constant. Okay? And the fundamental law is the conservation of energy. Now, what are some of the manifestations of energy? Work is a type of energy. Motion is a type of energy. That was kinetic energy. Position behind the dam, that was one. Lifting a book above the table, dropping it, that's energy of position, potential energy. Radiation, the energy coming from the sun is radiation energy, light energy. This time of year, the leaves are beginning to shut down, but as long as there are green leaves, they are taking that energy from the light and converting it into stored chemical energy. So there's chemical energy. The nuclear energy, the light from the sun, the radiation from the sun, came from major nuclear explosions happening on the sun, or we have nuclear energy here and on Earth as well. We have at least one nuclear power plant in Alabama, maybe more. Okay, I know Georgia has at least one and maybe more, and there's others scattered throughout the country. I'll skip over here. Heat is a form of energy. Mass itself, believe it or not, is a form of energy. And I think all of you are familiar with the equation that relates mass and energy. Even if you don't think you are, I know you've seen or heard the equation before. Anyone know what it is? If I named the guy who came up with it, you probably will guess it.
Benjamin Franklin.
Say again?
Benjamin Franklin.
No, not Benjamin Franklin. Einstein. That's it. Okay. This is nuclear energy. Oh no, mass itself energy. E is equal to mc squared. Now, E is the energy. M is the mass. Does anyone know what C is? No, it's a letter in the alphabet, but more than that. Huh? It is a constant, but it's a very specific constant. Which most constants, I guess, are very specific. The speed of light. You may have thought light was instantaneous. It's not. It has a finite speed. 186,000 miles in a second. Okay, 1 second, it traveled 186,000 miles. That's about 4.5 times around the equator of the globe in 1 second. It's pretty fast. It's very fast. So that's a huge number. Square that number and it gets even bigger. Then take maybe just 1 gram of mass or 1 kilogram of mass, multiply it by that enormous number, that's how much energy it has. It's total, just huge amounts of energy. That's what's going on with the sun right now. Mass is converting to energy. The sun is emitting nuclear energy constantly. Okay? We pick up just a little bit of it, the radiation from light. Okay. What are our sources of energy then? Well, the ones we use most often, petroleum, from which we get gasolines and oils and other things like that. Coal. In the past, that's been our major producer of electrical energy. Nowadays, it's going down as natural gas and other things are going up. Moving water, there again, the hydroelectric dams, that produces a fair amount, less and less of the percentage of energy we use is coming from that. Too bad. It's a nice, clean energy source, but there's very few places you can do it. Nuclear energy, not so clean, okay, but it's still it's cleaner than these earlier ones. Solar, beginning to be more and more useful. They mentioned moving water, moving air is now being used as a source of energy. Always has been with sailing ships, but they went out of vogue centuries ago. But now the wind farms are beginning to capture that energy of wind. Nice, clean energy with very small quantities being produced. What are our uses for the energy? A source, transportation, that's what y'all's business is. Generation of electricity, I mentioned that in several of these. Petroleum, coal, moving water, nuclear, all those produce, and even solar produces electricity. Heating, not quite so much needed today, but in a few weeks we'll be using more and more heat for that, energy for that. Cooling, a few months ago we were using big time energy for cooling. Lighting, of course, lots of different uses for energy. Okay. Any questions? All these forms move back and forth, glide from one to another almost seamlessly, but energy itself is neither created nor destroyed. You use it, but you don't create or destroy it. And how do we use energy? That concept is work, okay? Now, I know work is one of these terms that in everyday English has a lot of different connotations, you might say. In physics, a very specific definition. Work is the product of the applied force times the parallel distance through which the force acts. Okay? Now, I'm going to push on this chair. I'm doing work on the chair. Because as I push, it's strange here. My force is down this way. The chair, though, is moving that way. So the only force that I'm doing any work with is the component of this force that is in that direction. The force that I'm exerting downward is doing no work whatsoever on the chair. Only the component of the force that's in the direction of the motion. Okay? So it's the product of the applied force and the parallel distance through which the force acts. Either the parallel distance or the parallel component of the force. This guy picking up the box from the ground, his force is upward, he moves the box upward, force times the distance. That is the work he's doing. All right? Let's look at some of the units for that. First, let's look at here it is. The equation for it, work is equal to force times the distance. Understanding is the force and direct distance in the same direction. A force in a different direction or a displacement in a different direction, only one component of that. Remember, both force and displacement are vector quantities. Vector quantities. So the distance does matter. Brian, right? Okay. All right. So, in the U.S. customary system, the force is measured in pounds and the distance in feet. So what do we call that unit? Foot-pounds. Now, I'm making a guess here that many of you have used a wrench that was calibrated in foot-pounds, right? What do you call that wrench? A torque wrench, exactly. Torque is not work, okay? That's a different kind, okay? Torque is a vector quantity. Work, by the way, is a scalar quantity. It's a product of two vectors, but it's what they call the dot product. That's the product of the displacement in the direction of the force, or the force in the direction of the displacement in the same direction. If you think about the torque wrench, okay, the wrench is displaced. There's this nut or whatever you're trying to tighten or loosen with a certain amount of torque. It's over here. The wrench has a handle out to here. When you press on it in this direction, the torque is here. those are perpendicular to each other. So a torque wrench is a perpendicular, not a parallel force, and that is actually a vector quantity. That's the force, pounds, times the displacement, but perpendicular to each other. That is torque, a vector quantity. This is work in the same direction, a scalar quantity. So even though they have the same units, foot-pounds, they're different quantities, completely different quantities. Okay? Now in the SI system, Justin's here. In the SI system, the unit is force in newtons times displacement in meters. A newton meter has its own name, and that is a joule. Not the joule like a women crave or something like that. This is Joule, named after James Prescott Joule. So therefore that unit would be capitalized. Capital J for joule. Foot-pounds not named after anybody, so it's just foot-pounds. But a newton meter also has the name of joule, okay? And named after James Prescott Joule. Okay. Now, any questions on what work is, how you calculate it, how you name it, the uses of it, okay? Now, going back over what we just said, the units of work and energy, by the way, work and energy are really measuring the same thing. Energy is the ability to do work. Work is the use of energy, okay? They're equivalent. In the SI system, it is the joule, capital J, because it's named after a person. Now, let me give you an example, okay? When my wife and I bought the house where we currently live, it was a nice neighborhood. She really loved the neighborhood. We liked the house fine. We liked the lot. It had lots of trees on it. The previous house we had lived in, we sort of shared a tree with another on this side, one maybe back in the corner, but it had no trees on property. So we really liked it that we had trees there. But the previous owner, some previous owner, had put an extension on the back of the house. Big family room and a screen porch, okay? And in doing that, the house was on a hill, basically. And they had dug out a level place and built the house way back in the 1920s and 30s. But the hill went up here and then went down here. When they built in the back, they dug into the hillside to put that family room and screen porch back there, okay? So it made the house look sort of squatty, because at the back, the soil came right up below the windows, and the windows were really squatty windows, okay? So it looked a little bizarre, but the look didn't bother me that much. What bothered me is the water coming down the hill in the back just went right against the wall of the house, okay? Now that is creating some hydraulic pressure on that wall. Now probably that would be fine for a while, but at some point, more than likely, the water is going to start seeping through the wall, especially for very wet times and situations like that. The other problem, the soil came right up to the base of the windows. So you had very close to, and I found out actual, wood to ground contact. In the southeast, that's not a good idea. Anyone know why? Second? It'll rot. And what helps it rot is termites. Well, the moisture for sure, but termites, okay? Now I'm sure when they put that addition back there, they used treated lumber, which has, a poison in it, that's supposed to resist decay, rot, and termites. But in a while that leaches out. So you don't want wood to ground contact. So I said to my wife, well, if we wind up getting the house, we're going to have to do something to get the water to flow away from the house, not into the house, against the house, and also to get the level of soil down so you don't have wood to ground contact. Well, when we got the house and we mentioned that again, she said, good. I wanted a patio anyway. Not the scale of job I had in mind. I mean, I was just thinking of moving a little bit of soil, you know, berm and stuff like that. She wanted a whole patio dug out. Well, that summer, it was the first summer after I started working here, and that first summer I didn't have a full load. I just had the automotive students. Back then they had a special math called automotive math. I was teaching 2 sections of that, and they were on co-op programs too, but we were on quarter system, so they did 5 weeks and 5 weeks. You know, it was a 10-week term. So the first 5 weeks I was teaching 2 automotive classes. Second 5 weeks I had off. So in the first 5 weeks I started the process, and then in the next 5 weeks I started digging out the patio. Okay. Now, if you've done much digging anywhere in this area, I live in Birmingham, it's not long before you hit rock. Okay. Big rocks or little rocks, but you're going to hit rocks. And those were a pain. Okay. Like I said, we had lots of trees. So I didn't want to damage the trees, and I was trying to avoid the tree roots, you know, trying to get out from under the canopy to dig the patio. Still ran into some, but I tried to do as little damage to them as possible. But then I'd run into the rocks, okay? And most of the time, after a little bit of effort, I could get them out. But then just about the middle of the patio, I hit a rock just a few shovelfuls down into the soil. And the more I dug, the bigger the rock got. It just was uncovering more and more and more. I could not budge that thing, okay? So, when I was prying, cheater bars, everything else, sweating, putting a lot of effort into it, was I doing any work? No, because work requires a displacement. 0 distance, 0 work. I wouldn't have appreciated being told, nope, you're not doing any work, because I was sweating bullets out there, okay? Summertime, hot, dirty, nasty, trying my best to get that rock to move, but no matter how much force I put against the work, if I did no distance, no work, okay? Now, another situation, if the displacement is perpendicular to the applied force, again, you're doing no work, okay? Let's get this one in mind. Think of, remember when we were talking about last chapter, swinging the rock around your head, something like that, right? Now, you're exerting a force on the rock, that's what gives it the circular motion, it's the centrifugal force, right? But the force is this way, the motion is that way. Perpendicular to each other, you're doing no work. Even though you're exerting a force on the rock, you're doing no work to the rock. That is 0 work there as well. It has to be force in the same direction of the applied force. It has to be displacement in the same direction, not perpendicular to the applied work. Okay? Now, I'm going to push down on the chair. Not out, but down. I'm exerting a force on it. I can feel it. If I did it long enough, I'd start sweating. Am I doing any work on the chair? Absolutely none. Now, lifting up, yeah. Displacing upward, force times displacement, that is doing work. This way, doing work. But, if it's perpendicular to the force is perpendicular to the direction I want it to go, no work is being done. Okay. The sun pulling the earth around it, the earth pulling the moon around it. Those are perpendicular, displacement this way, force this way, no work is being done. Certainly force is being exerted, but no work is being done. Velocity is changing, but no work is being done. And here's Dimitri. All right. Now, here we've got a book next to the bottom shelf. We pick out the book and move it to the top shelf. Have we done work on the book? Yes, because the force is up, the displacement is up. The amount of work done is the magnitude of that force times the magnitude of that displacement, that distance. Okay? These are both vector quantities, both in the same direction, but the work is a scalar quantity, just the amount of work you've done. Okay? That, to me, should have been back on the previous slide, but it's fine here too. All right. I see no other slide here, but I think we are coming up on page 65, a couple of examples here. The question is, how much work? And by the way, if you haven't noticed yet, in your equations, work is a capital W. The parameter for work is capital W. You remember what little w stood for?
Weight.
Weight, exactly. Little w means weight, that's a force. Capital W means work, that's a product of a force times the displacement. In fact, here the force is the weight of the book, okay? So that is force, that's displacement, okay? Weight is a vector quantity because it's a force. Work is a scalar quantity because it's a product of two vectors, and it's called a dot product. The torque is a cross product, they call it, and that produces a vector. All right. So here we have how much work. So here's what we're looking for. Work, capital W, is needed to lift a 5 kilogram backpack, 5.0 kilogram. What's that a measure of? Mass, that's your mass, okay? On a shelf 1 meter above the floor. 1.0 meters. What's that a measure of? Distance or displacement, okay? Can we get work from those two quantities?
Yeah.
What is the formula? Work is equal to?
FD.
Second? Force times displacement. Is either of those a force? No. Okay.
But you can find force
How can you get the force?
by the formula force mg.
That's it. You're exactly right. The force here is the weight. Okay? Little w. To keep from getting them confused, I'm going to put F sub w for force due to weight. And that's equal to mass times the acceleration due to gravity. Because gravity is what gives it weight. So that's mg. So this is 5.0 kilograms. And what's g? 9.8 meters per second squared. And that gives us 49.049, what unit? Newton, or kilogram meter per second squared. Okay? So now we've got our force, the force due to weight, that's 49 newtons, times displacement of 1 meter. And what's our work? 49 what? Second? Joules. Or, if you go back to your fundamental units, kilogram, now it's meter squared per second squared. Because this is a kilogram meter per second squared, multiply it by another meter, you get a kilogram meter squared per second squared. That's what a joule is. Okay? So 49 joules of work. 49 newtons of force, but because you only move it 1 meter, that's 49 joules of work. All right. Let's go to the U.S. customary system. Okay. Again here, how much work, so again we're looking for work, that's your unknown here, is required to lift a 50-pound box. 50 pounds. What's that a measure of?
Mass.
Really? No, pound is a force measurement. That is your weight. Okay? See, we don't use mass units in the U.S. customary system. Anyone remember what it is? We never use it. Slug, exactly. That's not a slug, that's 50 pounds. That is a force unit. A 50-pound box vertically a distance of 2 feet. So 2 feet would be your distance. So what is the work done? Anybody?
The formula is F.
F sub W times D. And that would be 50 pounds times 2 feet. That would be, not hard, 100 what?
Joule.
Second?
Foot pounds.
Foot pounds, exactly. 100 foot pounds. Okay? Second?
Or joule.
I can't hear.
No.
Oh, yeah. But we usually say it in foot pounds, even though we usually multiply it and make it pound feet, but we call it foot pounds. Okay, does that make sense? Both of those were work units, foot pounds or joules. Okay? They're not the same quantities because this was actually a lot more mass than the previous. That was only, what was the mass? 5 kilograms. Pretty small. I mean, significant, but not bad. This is 50 pounds. So this only moved 2 feet, where the other moved 1 meter, which is at least 50% further that it moved. Okay? So, you can't really compare them too much. All right, so that's work. Any questions on work? Okay. Now, before we move to power, there is a blurb on page 66 and 67 on simple machines. Now, the basic premise here is that the work in equals the work out. Okay, that doesn't mean work out as in working out, but work in equals work out. In reality, that never happens. Your applied force is never, or work is never exactly the same as the output work. Input work is never the same. You always have some loss, inefficiency. No system is perfectly efficient. But that's what the premise is, that the work in equals work out. What we have is a thing called a force multiplier. You can multiply forces. You can't create work, energy, but you can multiply forces. Okay? It's multiplied by the ratio of distances. Let me ask you a question. Can any of you lift a car?
My car.
Regular size
Yes,
car?
my car.
I bet you all have. You happen to use a jack. And you did lift the car, didn't you? Okay, now think about that. Okay? You couldn't exert enough force by yourself to lift a car. But if you apply a small force over a large distance and move the car a very small distance, you are multiplying your force by that ratio of the distances. And you do that all the time, really, if you think about it. Here are some examples of devices, they're called simple machines, that use this concept. Back when we had done some work at the parents-in-law's lake house, later we bought it from them, I was having to haul around some pretty heavy blocks to build a retaining wall, okay? And a few of those places I had to get them up a hill. Most of it was downhill, but a few places it was up an incline. If I had had to lift those blocks up that would have been backbreaking. Okay, work. It would have been work for sure. But what I used was an inclined plane, and it didn't seem nearly as hard. Well, why? Because the distance over which I lifted those blocks only maybe 4 or 5 feet. I did it over a gradual distance, an inclined plane. It was much easier to do. Again, the inclined plane enabled me to multiply my force by the ratio of distances. That plane may have been, I had a big, long, seemed like it was probably about a 2x6 or 2x8 that was rolling up. And that was probably 8 to 10 feet long. So that 4 feet increase I did with a 10 feet thing, that was a 2.5 to 1 ratio. So I could do it with less force, but over a greater distance. Okay? Have any of you ever split wood? Okay, you grab your fingernails into the wood and pull it apart, right? I doubt it. Okay? You lose your fingernails that way. What do you use?
An axe.
A what?
An axe.
One more time.
An axe.
An axe. And what does an axe do?
Split the wood.
Okay, but how does it do that? It's a wedge. It has a sharp point, and then it gets further apart.
I'm sorry. You just have to hit it like this.
Yes, exactly. With the axe, exactly. And what you're doing the force is down this way. Your distance over which you move the force is pretty small, especially when you think you're splitting the wood this way. But it's a force multiplier, and you are indeed able to split that piece of wood with merely a force multiplier, a wedge. That's not what you did to your younger brother. Never mind, not that. Okay. A screw holds a lot better than a nail does usually, right? Because of the ridges. Well, if you think what a screw really is, it's an inclined plane wrapped around an axle. So sure enough, the force in which you're holding things together much stronger than if it had just been a nail nailed into it. It's just another application of an inclined plane, like a wedge is too. A lever, okay? You probably have all dealt with these before too. We did when we jacked up the car, right? That was a lever moving up and down like this a great distance, lifting the car a very small distance, but still a force multiplier. Okay? Wheel and axle, same type deal. Your axle is the thing actually turning, right? But the wheel's much bigger, force multiplier. Okay? So, and actually the axle is a lot more force than what's on the wheel. A pulley. Now there's a couple of different kinds of pulleys. If it's just one trip of the rope over the wheel, that's not a force multiplier. Okay? All you're doing is changing direction. You pull down, you lift up exactly the same amount. The thing you're lifting, the same amount you're pulling down. Not a force multiplier. That's just a change of direction. But if it goes up, goes around, and comes up again, now when you pull twice as far to lift it half as far, right? Because you have to pull twice as much rope to get it to go half the distance, right? That's a force multiplier. You actually can lift twice as much if you have that one time around. If you go around and come along twice, 4 times as much. You're multiplying your force by 2 every time you go around the lower wheel of the pulley. Okay? Have any of you, I've asked this I think before, I'll keep asking, have any of you been to the McLean Center? Okay. Do you know those seats over there? There's 3 of them. One of them, you just try to lift yourself. That's really hard. Okay, you're sitting in the seat, you're pulling, you're lifting. The amount you pull here, you're trying to lift yourself there. Really, really hard. Then the next one over here goes up, around, and down again. Much easier to lift yourself. The third one over there goes up around twice. Really a piece of cake to lift yourself with that. You do a lot more motion, but it's easier to lift yourself. Again, a force multiplier. And these are your simple machines. Okay? The basic premise is work in equals work out. Well, the work in is your force in times your displacement in. That's what work is. And the work out is the force out times the displacement out. If your work in, the force in, could be a fairly small force, as long as you move it a big enough distance, then you can move a big weight out a fairly small distance. That's jacking up your car. the product of the force N times displacement N equal. Now, if you divide both of these by the output distance, then this gives your force multiplier. Your force out is whatever force in, but then you multiply by this displacement in over displacement out, that's your force multiplier. You can exert 10 pounds of force, okay? That's not very much force. But if you move it 10 times as far here, you can lift 100 pounds of weight with that 10 pounds of force. Because if your ratio here is 10 inches out for every 10 inches that you exert in, 10 inches in for every inch that you lift out, you can multiply your force by a factor of 10. All right. You think this gal can lift 300 pounds? Doesn't seem like it, does it? Unless, of course, she has a lever. Okay? And with a lever, she can push down with only, I think that's 60. It's hard to read here. Yeah. 60 newtons. Okay. In the book it says newton. Here it says pounds. Pushing down with 60 pounds. That's not too hard for anyone to do, right? Okay? Pushing down with 60 pounds, and she makes an effort distance of 2.5 feet. Now, she moves the fulcrum way over here so that the ratio of her lever here is such that it's only going to lift half a foot, right? Even though she pushed down 2.5 feet. That's 5 times the input distance here than what the output distance is. But with that 60 pounds, 60 times 5 is 300 pounds she can lift with just 60 pounds of force. Yes, she can lift 300 pounds. Scrawny as her arm seem, she can do it. Okay? Archimedes was, one of his more famous quotes were, "Give me a lever long enough and a fulcrum to put under it and support it, and I could move the world." Okay? It sounds ridiculous, but if it was long enough, like enough miles long, and you had something to put that, yes, he could pick up, because if he had a long enough lever, the force multiplier would be great enough, he could move the world. Okay. Now there's another thing in this blurb. On the right-hand side of the page, it talks about several different kinds of levers. And you've probably used all 3 of them. The one is the one that just changes direction. You put the fulcrum in the middle and the weight on either hand, you're just changing direction. What was the playground toy that was called?
Seesaw.
Seesaw. Some people called it a teeter-totter. I never got quite what that was, but seesaw is what I always called it. Okay? That's one. All you're doing there is changing the direction of the displacement. Okay? The other one, though, and that, by the way, is called a first-class lever. The second-class lever, you have the fulcrum at this end, you put your effort here at this end, and you lift a much heavier load here than you were able to lift alone. Okay? Because you've got the load in the middle. What's an example of that kind? Say again?
Jet. Jet.
I can't hear you.
A car jet.
Car?
Jet.
A jet? Is that what you're saying?
Jet. Jet.
Huh?
Car jack.
Jack. Oh, a car jack. Okay, I'm sorry. Sorry. My hearing is so bad. Okay, a car jack. Yeah, that's pretty much that. I was thinking that certainly would fit there. But something is what I used when I was hauling those blocks. A wheelbarrow. Your fulcrum is there at the wheel. The bed is where you put your load. You're out here at this end, your effort. I could lift and move a lot more blocks in the wheelbarrow than I could do by hand. Big time more. Okay? That was another one. Car jack would work too. Now the other one, you put the fulcrum at one end, put the effort in the middle and the load at the other end. Here's the fulcrum, here's your effort, and there's your load. What is that called? I used it when I was digging out the patio. A shovel, exactly. There I'm not lifting nearly as much as a note, but I can move it at a like greater distance. There your distance is being multiplied, not the load, the force. Okay? You're actually multiplying the distance. That's called the third class lever. Second class would be like the wheelbarrow or the car jack. Okay. Those are your simple machines. Now we're ready to do power. The term that y'all were saying work and energy was. No, not quite the same. Now let's step back a minute. Go back a few weeks when we first started the class. One of the first things we talked about was distance or displacement. Okay? That's part of motion, right? You move something a distance, you displace it. Okay? And then the way to describe that is to talk about the time rate of change of that displacement or distance. And what do we call that quantity?
Speed.
Speed or velocity, exactly. So once we got that down, what's the time rate of change of velocity?
What?
Time rate of change of velocity.
Acceleration.
Acceleration, exactly. So that's what we typically do in physics when we have a good quantity that we understand and work. Well, then let's take the time rate of change and see if we learn anything with that. And that's exactly what we did. Now, in the last chapter near the end, we were talking about Newton's 3 laws of motion. I said Newton really didn't talk that much, I don't think, about forces, but he talked about this quantity of motion, which we call today momentum, exactly. Mass times your velocity, okay? And then if you did a time rate of change of momentum, what was that?
Input.
That is the force. Time rate of change of momentum. I think that's probably how Newton referred to it, time rate of change of momentum. Not a force, necessarily, but time rate of change of momentum. Well, we've been talking about work, we've been talking about energy. Well, let's take the time rate of change of that, and what do we have? Power, the rate at which work is being done, or the rate at which energy is transformed. Okay? Now let's get back to the patio. Okay? That summer, for those 5 weeks after I finished teaching and before we started back for fall term, I was digging out that patio and running around that rock. Okay? But anyway, when the 5 weeks were over, I had basically just about half the patio dug out. That's all, folks. That rock was really a time killer. And it had worn me out, too. Well, by this time, though, I had enough area opened up that you could get a bobcat in. And I wonder if any of you are wondering, why did he use a bobcat? There wasn't space, there wasn't room to maneuver a bobcat. But by the time I got it about halfway dug out, now you had room to get a bobcat in there and move the soil around. So here it was, the weekend before Labor Day. We were coming back for fall term right after Labor Day. No way I was going to finish digging out that patio just on weekends. If it had taken me 5 weeks of pretty steady digging to get half of it done, and there were a few rainy days, a few days I had other things to do, but by and large about 5 weeks. Okay? And I had gotten about half of it done. Well, we hired this bobcat to come in, and in half a day, he moved the other half of the patio, moved the soil for that. What was the difference between me and him? The amount of work done? No. I did half of it, he did half of it. What was the difference? The time. It took him half a day. It took me 5 weeks. Okay? The difference is his bobcat, I'm guessing, was probably 200 to 300 horsepower. Me working alone, considerably less than half a horsepower. Okay? Yes, the power was the difference there, and that was based on the time. The rate at which work is being done, we did the same amount of work, he just did it a lot faster than I did. So here's the formula for power. Power is equal work divided by time. The time rate of change of doing work or expending energy. All right. Now, way back, seems like it was probably around the maybe 18th or 19th century, there was a Scottish engineer named James Watt. Okay? And he defined one of the first units of power as the amount of work a standard dray horse, those are the big hefty ones, working horses, not the riding horses, but working horses, could do in a day. And he named that 1 horsepower. Okay? And in a second, that would have been 550 pounds, that's the force, times the distance of 1 foot, that would be 550 foot-pounds in 1 second. And multiply that by 60 seconds to make a minute, 60 minutes to make an hour, and 8 hours, say, to make a day. That would have been 1 horsepower. The amount of work the dray horse would have done in a day. Okay? But breaking down to seconds, 550 foot-pounds per second. That's 1 horsepower. Okay. Work, foot-pounds, force times of displacement, divided by time, and that gives you power. Now, I know in previous classes with a lot of automotive students in it, y'all use power to mean just about everything. Okay. No. Work is one thing, power is a different thing, force is a different thing. So be careful with your terminology, especially in this class. In your automotive classes, you can do whatever they allow you to do. Okay, so again, it's the rate at which work is done. In the SI system, when they got around to having this system, he preceded the SI system. When they got around to having it, they named the unit of power after James Watt. So what's the unit for power in the SI system? What? 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 Yeah, a watt. Okay, never mind. Okay. Watt. Capital W because it was named after somebody, James Watt. He defined horsepower in the U.S. customary system, and that was 550 foot-pounds per second. Okay? Now, today's lab is going to do this. We're going to go to some stairwells, and y'all are going to walk up the stairwell, timing yourselves, okay, and doing the calculations, and then you're going to run up the stairwells. Carefully, safely run up the stairwell, measure the time, and calculate your power then too. You're going to do the same amount of work, going from this level to that level. That's the work done. It doesn't change. As long as you don't lose a lot of weight doing it, it's going to be the same force, the same work. But the time is going to make the difference, okay, in power. Now, before we get to that, here is the picture of this. And when you walk up the stairs, you have to look really forward like this, just lingering up the stairs. Now, is the horizontal distance contributing any work to the situation? No. Because work is force times displacement. Your displacement's upward. Displacement this way, you're not doing really any work. Because gravity is pulling down and you're going this direction, that's perpendicular. That's not doing any work. It's only the height change that you have that's against gravity. That's the amount of work you're doing. Okay? If this guy weighs a certain amount, mg, and goes this height, h, this is the amount of work he did. Whether he walks up the stairs or runs up the stairs, the work is the same. The energy expended is the same. What's the difference is the power is greater here than here because this takes him longer, this takes him a shorter time. So there's increased power because it's inversely proportional to the time. Does that make sense? This is what you'll be doing in lab. Pretty fun lab. Won't take you that long to do, okay? But I want all of you that can to do it, okay? Now, when, I don't know if y'all take care of your own building or not, or do you still live at home or whatever, I don't know the situation there. But when the electric company sends your bill, what are you paying for? Say again? You're paying for power? No. You're paying for energy, not power. Okay? You're paying for the energy you've used. Even though it's called Alabama Power Company, it's not power. You're paying for energy. Now, if you remember what power is, remind me. Work or energy divided by time. Okay? Now, if you ever notice, do any of you even see those energy bills?
Yeah.
Or is it mom and dad taking care of it? Oh, you're taking care of it. What are you paying for? Do you ever notice what you're paying for?
Yeah, what? Consume.
You're not paying for watts or kilowatts.
That, like, the time period we use.
Okay, it's the time you've used it. What you're paying for is multiply both sides by time, and you're paying for the energy or work, which is power times time, and what you're paying for is kilowatt hours. Go home and look at the power bill. It's not paying for power, you're paying for work. Work is kilowatt times hours. Okay?
Excuse me, so that's the room service, just go look at the power bill?
If you want to, you can do that. And you'll see what you're paying for is how many kilowatt hours of energy you use. Not how many kilowatts you use, how many kilowatt hours you use.
Do we get bonus points?
What's that?
Do we get bonus points for doing it?
No, that's just for fun, okay? Just for fun, okay? It's all fun, okay? There's a little example in the book here. Let's just say a 120-pound person. I don't even remember when I was a 120-pound person. That's a 120-pound person. What's that a measure of? What is that a measure of? 120 pounds. Say again? Anyone? What'd you say? Weight, which is a force. Okay? And you move a height of 10 feet, up 10 feet of stairs. What's that a measure of? That's your distance. And it takes you 4 seconds. What's that a measure of? Time. Okay? How much power did you expend doing that?
300.
Okay? 120 times, that's pounds, times 10 feet, that's foot pounds. 120 foot pounds divided by 4 seconds, that's a 1,200 foot pounds in 4 seconds. Divide that, 300 foot pounds per second. Now, if you wanted to calculate how much horsepower that is, divide by 550. And it's a little over half a horsepower. Okay? A little over half a horsepower. Okay. But foot pounds per second, perfectly good unit of power. Now, what if the person only took 3 seconds to go up that same flight of stairs? The amount of work is still the same. 120-pound person, 10 feet, still 1,200 foot-pounds of, oops, I didn't put my pounds there, foot-pounds of energy done, work expended, but it now took 3 seconds, so what would that have been? 400 foot-pounds per second. So more power, same work, same energy, but more power, 400 foot-pounds per second. And that would be about 7/10 of a horsepower. The other was
Excuse me. So that's 300 foot/second.
right. At first I started with, the first one was when you did it in 4 seconds, that's 300 foot-pounds per second. When you did it in 3 seconds, that made it 400 foot-pounds per second. It's just showing the difference. If you do it in shorter time, it takes more power to do it. Okay. Now, what's the unit for power in the SI system? No, that's energy, or watt. Okay, watts. Okay. And that's 1 Newton of force times 1 meter of displacement in 1 second. That is 1 watt. And by the way, 1 watt is a very small amount of power. A Newton is not that much force. A meter is a reasonable distance. 1 second is not that's only 1. We usually measure a lot of things like electrical in kilowatts, not in watts. Okay, that would be the power expended in kilowatts. Okay, a guy, they show a picture in the book, easily can lift 1 Newton, about 0.22 pounds. A little over between 1/5 and 1/4 of a pound. That's not much force. 1 meter, which is a reasonable height, a little over a yard, in 1 second. That's easily doable. All right, let's do example 3.3 on page 68. All right. An electric lift can raise a 500 kilogram mass. 500.0 kilogram. They told you what that was. What is it? Mass. Okay. A distance of, they told you what that was. Distance of 10.0 meters. Okay. Now, don't get these confused. I put my units over here and put the parameter mass here, then I put the parameter distance here with the unit meter there. So don't get those confused. In 5.0 seconds. What's that a measure of? That's your time. Okay. What is the power of that lift? So what we're looking for is power. What is power?
Work over T.
Work over time. Okay. What is work?
Force.
Force times displacement over time. What is force?
500.
Mass times acceleration due to gravity. That is your force times displacement over time. So for this problem, what is it? 500.0 kilograms times 9.8 meters per second squared times, what's your displacement? 10.0 meters in 5.0 seconds. Okay? So, let's see what we've got here. Let's do the simple thing and divide the 5 into 500. That would be 100. That way you get rid of your denominator. Okay? And 100 times 10 is 1,000 times 9.8 would be 9,800 kilogram meter squared per second squared per second. Yeah. That would be 9,800 joules per second. And what's that?
Hour.
What would be the unit for it?
What?
Watt. 9,800 watts. Or, to make a smaller number but a bigger unit, that would be, make the number smaller, give it a bigger prefix, Yes, how many? 9.8 kilowatts. Yep, that's how much power you're using, measured in watts or kilowatts, 9.8. Okay. Now, for some reason, they said, let's get that into horsepower. Now, the slideshow didn't show us this, but back on page 66, I believe is where it is, yeah, here are some conversion factors for you, okay? I'll put them at the top. Remember, a watt is a very small amount of power. A kilowatt is a significant amount of power. What would be a million watts? What would we call that? A megawatt. That's what we measure power stations with, power plants. So many megawatts of power they're producing. So many joules per second. Megajoules per second, okay? They also measure bombs, okay, in megawatts, especially nuclear weapons, okay? Pretty big, okay? Now, here is the conversion that we need here. It takes 746 watts is equivalent to 1 horsepower. So see, a horsepower is way, way, way bigger than a watt. But it's less than a kilowatt. So how many kilowatts would that be? Move the decimal 3 places. 0.746 kilowatts would be equivalent to 1 horsepower. Okay? In other words, about 3/4 of a kilowatt is 1 horsepower. So a horsepower is much bigger than a watt, but a little bit smaller than a kilowatt. Okay? 3/4 of a kilowatt approximately is 1 horsepower. Okay. So back on this problem, if we have 9.8 kilowatts of power, how many horsepower is that? 9.8 kilowatts. We need to multiply by our conversion factor, and we're trying to get the horsepower. Now, I put 2 blanks there. The first blank is for numbers, the second for units. Always put what in the place? The units in their place first. Okay? And which unit will go where? You got 2, kilowatts and horsepower. Which one are you going to put where? Anybody?
Kilowatt at the bottom.
Kilowatt on the bottom, horsepower on top. That way you're going to get it. The kilowatts will cancel out. Now, I just gave you the conversion. How many horsepower in a kilowatt, or how many kilowatts in a horsepower? 0.746 kilowatts is 1 horsepower, right there. Okay, so you take your 9.8, divide it by 0.746. Someone has a calculator? What you get?
13,136.
Okay, sounds a bit high. You're in watts, I think. 13 point what?
13.13 watt.
Yeah, 13 point what?
13.
13, yeah. Not watts, horsepower.
Yeah.
That's about 13 horsepower. So 9.8 kilowatts would be about 13 horsepower. Round it off, So they're in the same ballpark. A few more horsepower to make equivalent kilowatts. Okay, does that make sense? All right. Now, let's go back to the stairwell and do a calculation there. 150-pound person. Been a long time since I've been a 150-pound person. I don't even remember it. Runs up a 15-foot stairwell. 150 pounds. What does that measure? That's a force, your weight measurement, force, okay? Runs up a 15-foot stairwell. What's that? That's your distance, okay? In 10 seconds. That's your time. What is the horsepower rating of that person? So what would you do? What is power?
Work over 3.
It's what? Work divided by time. And what's work?
Force.
Force times displacement over time. And now we got everything. Got the force is 150 pounds. Displacement is 15 feet. And your time was 10. Bizarre, they put 10.0 seconds. Okay? Now, 15 times 150, I think is 225, huh?
Yeah.
2250? Is it?
Yeah, 225.
Yeah, but it's 220, it's 2250. 15 times 150. 15 times 15 is 225, but you got another zero on it.
But we have to divide by 10.
Oh, okay. Okay, you're doing foot-pounds per second. I was doing work. That would be foot-pounds divided by 10.0 seconds.
Yeah.
This is foot-pounds. I keep forgetting to write the pounds. That's 225 foot-pounds per second. That's the amount of power expended. Work per unit time. Okay? But it's asking for horsepower. What was the conversion for horsepower? Blank blank equal blank HP. Now this is a different conversion from before. Before we're doing watts to horse or kilowatts to horsepower. This time we're doing foot-pounds per second to horsepower. What was that one? What unit do we put where? Foot-pounds per second in the denominator and horsepower in the numerator. And what was the conversion there? Do you remember?
Of what?
It was 550 foot-pounds per second is 1 horsepower. Remember, that's what James Watt determined. So take 225 divided by 550. What do you get? Anybody?
0.40.
4.1, right?
Yeah.
4.1 horsepower. 41 hundredths of a horsepower.
8 has 9. 0.409.
409, so you take the 9 and round up the thing. The reason we do that is this was 3, well, we don't know if that's 2 or 3. That's only 2. This was 3, but you always go with the smallest. So keep all the units for a while, but at the end, round to 2 units. So the 9 makes the 0 become a 1. Okay. 0.41 horsepower. Any questions on that? All right. How are we doing? Hey, doing pretty well. All right. We just have time to start motion, position, and energy. Okay? Now, what we're talking about here is we're moving from work, which is the use of energy, and power, which is the time rate of change of work or energy, to the various forms of energy. Okay? So, work and energy are definitely related. They use the same units. Let's see a definition or two. Okay? Energy is the ability to do work. Okay? The ability to do work. That's what energy is. Whereas on the other hand, work is the process of changing of things' energy level. Okay? Now what do we mean by that? Let's take this book right here. I'm just going to make an estimate that this is about a kilogram or so of mass. Okay? So how much weight would that be? If it was 1 kilogram, what would be its weight? 9.8 kilogram meter per second squared, which would be
Newton.
About 9.8 newtons. So let's just call it 10 newtons. This is 10 newtons of the book. That is its force, its weight. Now I'm going to lift it about a meter, okay? Would that be about a meter? I think so, from the desktop to here. So now I've done about 10, what unit? Joules of work. Newton times, I'm tired of holding it up there, 10 newtons of force times 1 meter of distance will give you 10 joules of work that I did. Now, I took energy to do that work, okay? The work was the process of changing energy level from here to there. So that's how energy and work are related, okay? It's the energy is the ability to do work, and work is the process of changing an object's energy level. You can do positive work by increasing the energy level, letting it do work on you, decreasing the energy level. Okay? Now, next, what is the relationship between work and energy? A lot of times it's associated either with position, and later we're going to deal with it with speed. Okay? So the relationship between work and energy that's associated with position, that is called, and then later we'll do the relationship between work and the energy of motion. This is called, especially if you're talking about position above or below something, gravitational potential energy, or generally potential energy. This is the work relationship between work and the energy of motion. That is kinetic energy. Okay? So if I lift the book 1 meter, I have done 10 joules of work. Okay? If I throw the book, okay, from rest to, say, 10 meters per second at you, I am giving it kinetic energy, energy of motion. So we have 2 different types of energy depending on whether you're just changing its position or you're changing its speed. Okay? Its motion. Okay? And we'll be talking about those 2 in the next section. So let's introduce at least potential energy. Now they call it potential energy, the energy associated with position, and specifically we're talking about gravitational potential energy, because that's what we're working against, is the force due to gravity. Okay? Now, whenever you're talking about potential energy, you have to have a 0 reference level. Okay? The important thing is how much that is changing. It's not where you actually began. So you need to know what you're measuring from. You need some reference height. If the desktop was my reference height, yes, I did 10, gave the book 10 joules of potential energy. But if the floor was what I was referencing, that could have been 20 joules of potential energy from the floor. If I held it out the window there and measured it from the ground level, then that's even more potential energy I'll get. So you see, you need to know where you're measuring from. In other words, what's your 0 reference level? If we did it above sea level, that would be even further. Okay? So you need always to identify what you're referencing the height. And here's what my little rule of thumb most of the time is. Measure it from the position that's as low as it will go in that situation. So when we're doing the next lab, that's going to be comparing potential and kinetic energy, we're going to see what's the lowest position this object can have. That'll be my 0 reference level. And then we'll measure everything above that. Okay? Now there's other types of potential energy. One is elastic or spring potential energy. That's the compressing or extension of a spring. You have them in your cars. You have them in all sorts of things. That's spring potential energy. That's also a displacement, energy associated with a position. If you compress the spring's pushing back at you. If you extend the spring, it's pulling back at you, okay? So that's a potential energy there. Now, you have electrical potential energy. We'll talk about this in Chapter 6, and that will be from some 0 reference level as well. Y'all call it ground. Okay, that's okay as a potential reference. We also have chemical potential energy. That's what those little leaves are out there doing. When the sun shines on the leaves and they're exchanging the ATP with ADP and doing that kind of stuff, they're taking water from the soil, carbon dioxide from the air, and making simple sugars, storing the energy that they're doing in chemical potential energy. So there's all kinds of potential energy. We're going to focus mostly on gravitational and a little bit on elastic. Chapter 6, we'll talk about electric potential energy. All right, let's finish this slide. Now we'll start on this slide, because that's a little bit more to talk about. Okay. We will begin with this slide next time. Okay. I'm going to take this home with me today. All right. What I'm going to do now is pause the recording. Modification. What it says to do is measure the height of one stair and multiply. Well, the stairs may not be uniform height, so that's sort of in a difficult way. Okay, is everybody in here? There's still people up in the classroom. Demetric, are you going to come in? Okay. Is there anybody left upstairs? Okay. So what we're going to do, rather than measuring the height of one stairs and multiplying, what I want you to do is put the base here, and then remember we're going in feet, not meters. So 3 feet is 36 inches. So right there is 36 inches. From there, you will go up and another 3 feet. Now at this stage, you need to move over. So you're right about the middle. No, you're right about there. So move over on this block until you're somewhere about there. I'm not doing it exactly, okay? About there. And there's another 3 feet to 36 inches, okay? And then go from there. I can't do it holding my computer. And measure how many. So I want you to estimate to the nearest foot how far it is from there. Now, if you'll come up here for just a minute, or you can probably see. Do you go to the top of this right here? No, because the floor is somewhere down here. You're going to have to estimate where the floor is, because you're going from floor to floor, not to the top of here. You're not going up on that. So do your to the nearest foot from that floor to wherever the floor is here. And you can judge that by the blocks, that you see coming down here. So measure to the nearest foot how many feet that is going to be. Okay? Now, who has a stopwatch? Oh, I meant to take this out of the box, so I'm going to take it out. Okay, here. Okay, I got one. Okay. The person with the stopwatch is going to be located here. Okay? Okay. Now don't be playing with these too much, because if they get on the wrong mode, it's going to be really hard to do your measurements. So remember, start is at 10 o'clock. Start. Stop. That was 2.6 seconds. No one's going up the stairs in 2.6 seconds. Reset is over here at 10 o'clock. Reset and go back to 0. So the first time, now let me go down and illustrate this again. Now, I'm not going to do it too fast because I don't want to drop my computer. But the first time, each person is going to walk up the stairs. Just at a casual pace, walking up the stairs. The person up here will start the stopwatch when they make the first step, turn it off when they make the last step. Okay? Measure how many seconds. That goes on the sheet. The second time, each person will do this. The second time, you'll run up the stairs. Now, what do we mean by running up the stairs? Running safely up the stairs. Not as fast as you can, as at a safe speed. Now, this is just going to be an approximate. Just something faster than a walk. That would be fine. I've got a bad knee, so I'm not going to do the whole thing. Okay? And then you take the time too. Whose watch was this? Okay. All right. Now let's look at your data sheet. Your data sheet on the very back page, the first thing you have is the weight. Now, if the gals are all together, you can do whatever you want to with the weight. The guys, I guess you know approximately what your weights are. So, is the weight going to change between walking and running? No. So you'll put the same weight down. Now, will it change between volunteer A and volunteer B? Probably. Okay? Now, if you have 3 people in a group, or even 4, the third person can be out here on the right-hand margin, the fourth person over there on the left-hand margin. You can do it. Everybody can do it if you wish. If anyone does have an issue, like I have a bad knee, if I could get out of it, I probably would, but you know, you don't have to. It's going to be fun to do. So your weight, you've measured the vertical height that you're traveling. That's going to go next, and that's going to be the same in every measurement, right? So once you measure that once, you have it. That's the first thing to measure. I'm going to take 2 groups that have the meter sticks and assign you to stairwells. Then I'll take the other 3 groups and assign you to stairwells. I'll come back and get the meter sticks and get them to you then. Okay? So, that's why if you got the stick first, you get finished first. Okay. Then you do the time, first to walk the steps, every person, and then to run the steps. Safely, every person. Once you've done that, go back to the classroom. We'll do all the calculations in the classroom. Just you do your weight, your height, the time to walk, time to run, every person, and then come back to the classroom. Okay, which group is going to be at the stairwell? Is that you? Who's with you? You need somebody with a watch?
3.
Okay, you got a watch?
Yep.
Okay, is that the 4 of you?
Yes.
Okay, the rest of you come this way. That 4 will stay here. The rest come this way. Okay, you got a meter stick?
I do.
Okay. Okay, the team with this meter stick come with me. The rest of you stop right there. Have you got a stopwatch?
Yes.
You do? Just one, right? Okay. Okay? Again, what you're measuring is from the floor here to the floor up there, not the top of the wall. Measure that first. I'll come back and get your meter stick. Okay? Remember, you're not doing meters, you're doing inches. Okay. 36 inches, 3 feet to the closest foot. Okay? The timer will be on the middle stairwell there, so you can see when you start and when you stop. Okay? I'll be back in a few minutes to get your stick. Any questions? Okay. Okay. All of you, come this way. Is everybody still here? Okay, come this way. You go through here, hang a right. And stop at the next stairwell. We got everybody?
There's one in the bathroom right now.
Okay.
Which stairwell?
Okay, come on around. Just you'll find us.
Okay.
Okay, come this way. Okay. All right. The ones with the meter stick, stop at this first stairwell. The rest of you, hang tight, and we'll keep moving. Okay. 3 people here? Okay, let me get with them for just a second. Okay, y'all got a meter stick? You got a stopwatch? Okay, then what you'll do, you measure, you'll have to go down there, you measure up that wall to the floor level, not the top of the wall level. Measure to the nearest foot, how far it is, then the person with the stopwatch will be here to mark when you start and when you stop. Okay, any questions? All right. All right. We should have 3 more teams, right? 3, 6, 9? 3, 6, okay, we got them? Okay. Come on. Sorry. Okay. 3 people here, and you need a stopwatch. Y'all got a stopwatch? Okay. The person with the timer will be here. You'll measure on that wall from the floor to the floor up there, which is not the top of that wall, but there. I got to get you your stick. I'll get it in just a few minutes. Okay? The other 6 of you come here. Okay? If 3 want to stop here, 3 follow me. I need the 3 with a stopwatch here, 3 with a stopwatch stop there. We're missing 1. Okay.
Hey, you were the... Yeah.
Have y'all got a stopwatch? Okay, good. Okay? This is your stairwell. This is your stairwell. When I get you a meter stick, you'll measure from the floor there to the floor up there, not the top of the wall. And the timer will be here with the stopwatch. Okay, I'll be back with the stick in just a minute. Okay, wait. You're only supposed to be 3 in this group. Okay, you're with these. Come on. Okay. All right. You got 3 left? All right. Yours is the last stairwell. I'll get your meter stick in just a minute. I'm going to set down my computer, I think. Okay, can y'all make it? Okay, here's your stairwell. You'll measure along that wall from that floor down there to the floor at the top. Not the top of the thing. Now, you got that big old thing in the way. Sort of work around it. I think you can do that. Estimate and do the nearest foot. I'll get your meter stick in just a minute. The guy with the stopwatch will be here, timing when you start, when you stop. Okay, I'll be back in just a minute with your meter stick. All right. Okay. So everybody got a weight. Volunteer A, volunteer B, either C or D, whether you got those or not. Should be the same weight walking and running for volunteer A, same weight walking and running for volunteer B. Right? Then the vertical height, all of the teams measured that to the nearest foot. That should be the same all the way across the board there. Right? Okay. The time required to walk the flight of stairs, volunteer A should have a time, volunteer B should have a time, C or D if you did those. The time to run the flight of stairs, a time for that, for A, a time for B. Now, let me make sure on this, folks. The time for running for every person is less than the time for walking, right? Good, okay. Now, how do you determine the work done? How do you determine the work done? Second? And what's the force? The weight times the distance, the height of the stairs. So everybody got that, right? What's that unit measured in?
Joule.
Second?
Joule.
No, it isn't. Look, foot pounds, okay? Right? We're not converting to we're using foot pounds. Weight in pounds times vertical height in feet, that's foot pounds. Okay? Now, that's your work done. How do you get the power?
Work done here at that time.
Yes, the line above, the work, divided by the time. Now that's the time that is above there. Not any old time, but the time that's right above. Now, the next question, how do you get horsepower? Oh, and what would be the units of power?
What?
Huh?
What?
No, it isn't. This is U.S. customary. What was your work done? Foot pounds. Your time was in seconds, so it's foot pounds per second. So that next to the bottom line, the power is in foot pounds per second. Right?
And you do what on that?
Second?
You do that what? What do you do to get that?
Okay. The work done on the third to the bottom line, that's your weight times your displacement, your vertical distance. Okay? Then you divide that by your time, whether it's either the time to walk if you're in the first column, time to run if you're second column, time to walk in the third column, time to run in the fourth column. And that would be, the units are foot-pounds per second. Then, how do you get that last entry?
The power divided by 550.
Okay, whatever your power divided by 550, and that will give you what units?
HP.
HP, horsepower, or Hewlett-Packard 1. Okay, you will. Okay. Got it?
Yeah.
Has everybody done the calculations? And preferably done them correctly. Now, let me make a guess. Just a guess here. None of you walking got probably very close to a horsepower, did you? Should be a pretty small number.
Yeah.
A decimal fraction, right? Okay? Now, a few of you running, depending on how fast you run, you may have gotten close to or even exceeded a horsepower. Did any of you? But you certainly got closer than what you did walking, right? Okay. Okay? Now, is everybody finished with the calculations? Okay, there's still a few people working on it, so let's give them time. And y'all are a team, you can work together, compare notes, make sure you got the right, that you're all in agreement, and no one's got something really wacko. Is this a track star I see here? You should have had a track. Huh?
It's been a few years.
No,
Quite a few.
I mean yours.
Yeah, it's been a while.
Oh, I see. Okay. All right. We had a ringer over there. Okay. Okay, is everybody finished with the calculation? Okay. Did everybody get for your horsepowers, especially the walking, a pretty small decimal number, and then the running a little bit larger? Maybe even exceeded 1. I don't know. A few times with. Okay, let's go to the results on page 126. Every one of these needs to be answered. Explain why there is a difference in the horsepower developed in walking and running up the flight of stairs.
Because running time is shorter and
Okay, the big deal there is the time. Yes. Okay, I'll let y'all word that however you want to. That second question, though, always gives people a few problems. So let's read it and talk about it. Is there some limit to the height of the flight of stairs used and the horsepower developed? Now, we just did one story, one flight. Do you think there would be some limit to the height and the amount of horsepower you developed? Okay.
I mean, the longer you go, I feel like sometimes you get more tired.
Exactly. What if you were running the stadium at Bryant-Denny or the one down here, okay? Do you think you could maintain that same rate? I doubt it. So yeah, I would say there is a limit. You know, physical limit to how high you could go without passing out or something like that. I'm glad we didn't have that pass out. Nobody had any injuries, right? Good. All right. Now, the Auburn is Jordan Hare, isn't it? I couldn't remember. Yeah, Jordan Hare safety. Okay. I didn't want to just favor. Or even Legion Field, okay, for UAP folks. Okay. Or the Talladega grandstands. That would be quite a few stairs, wouldn't it? Don't think you could maintain the same rate that you did in one flight. Okay. All right.
70 years
Now, how about question 3? Has anyone thought about that one yet? Could the horsepower developed by a slower moving student ever be greater than the horsepower developed by a faster moving student?
Yes.
Why? How?
Weight.
Yes, if the slower moving student was heavier, had more weight, and wasn't that much slower, he could produce more horsepower. You're absolutely right. And I bet you some of you in your teams, if you compared notes, you would see that a couple times a slower time still produced greater horsepower if the person at that slower time was a bit heavier than the others. And then number 4. Describe an experiment you could do to measure horsepower you could develop for a long period of time rather than a short burst up a stairwell.
Running a mile or something like that.
Okay? Now, a lot of times people do that, say that, but if you're running a mile, it shouldn't be on a flat track because you have no elevation change. So if you run a mile up and down hills, yeah, that might do it. Okay? Or up and down a stadium or something like that. Yeah. Make sense? Okay, and number 5, you better answer it. I don't care how you answer it, but you need to answer it. Are there any questions before I turn off the recorder? I don't know if any of you are familiar with Southside Birmingham, but I guess if you thought about it, you could run up Red Mountain. That would be a pretty tough thing, measure the time for that. All right. Can I turn off the recorder? Any other questions you think? Everybody feel pretty good about it?